Welcome to Digital Skill Lab.
Every single time you click a mouse, swipe on your phone, or do pretty much anything on a computer, you're triggering billions of microscopic switches. They're called logic gates, and they are the secret language of our entire digital world. So in this explainer, we're going to pull back the curtain and see exactly how they work.
But seriously, how is that even possible? How can a little piece of silicone make billions of complex decisions every single second? That's the big question we're going to tackle today. And you might be surprised to find out, it all starts with a really, really simple idea.
All right, so to get a handle on the tiny world of logic gates, we first need to zoom way out. We need to look at the most basic model of what any computer is actually doing.
At its core, every single computer, from a supercomputer to your calculator, just follows these 3 steps. You give it some kind of input, it does some process, and then it gives you an output. But here's the thing. All the magic, the entire secret to how computers seem to think, is hidden right inside that middle step, the process box.
So let's dive in. We're going deep inside the computer's brain, the processor, to find the tiny little components that are in charge of all that decision-making. These are the real gatekeepers of information.
And here it is, a logic gate. It's really just a microscopic switch. Its whole job is to control whether electricity can pass through or not, and it does that by following one simple rule. Think of it like a tiny security guard at a door who can only ever say yes or no.
And this is where things get absolutely mind-boggling. We're not talking about a few of these switches, or even a few thousand. A single processor chip in your phone has billions of these logic gates crammed into a space smaller than your fingernail. It's incredible.
So how do all these billions of gates talk to each other? Well, they use the simplest language possible, electricity. A signal is either on, which we represent with the number 1, or it's off, which we call 0. And that's it. That's binary. Electricity flows into the gate as an input, the gate applies its rule, and then it sends a brand new signal out as the output.
Now, what's amazing is that all the complex stuff your computer does, from playing a video to calculating a spreadsheet, it's all built from just a few of these simple rules. So let's meet the 3 most important ones: the not, the and the or gates.
Let's start with the absolute simplest one, the not gate. I like to call this one the opposite gate because its rule is just so easy. Whatever you put in, it gives you the exact opposite on the way out. Okay, so check out this chart. This is called a truth table, and it shows us exactly how the gate works. Look here. If the input is a 1, on, the not gate flips it, and the output becomes a 0, or off. And of course, if the input is 0, the output becomes 1. It's a perfect little inverter. And when engineers draw circuit diagrams, this is the symbol they use. It's a simple triangle with a little circle on the end. That circle is the key. It always means invert, or not. Okay, next up is the OR gate. This one's a little different. It takes 2 inputs, and its rule is way more inclusive. It'll give you a 1 on the output if the first input is 1, or if the second input is 1, or even if they're both 1. It's pretty generous. Here's a super simple way to think about it. Let's say Marcus will have something to eat if he gets an apple or a banana. So, if he gets an apple, does he eat? Yes. If he gets a banana, does he eat? Yes. And if he gets both, well, he definitely has something to eat then. The only way he doesn't eat is if he gets neither. And the truth table proves it. Just look down that output column. As long as there's at least 1 1 coming into the gate, the output is going to be a 1. The only way you get a 0 is if both inputs are 0. The official symbol for an OR gate is this kind of curved shield-like shape. You can see the 2 inputs flowing in from the left and the 1 output flowing out on the right.
All right, on to our 3rd and final gate for today, the AND gate. Now, if the OR gate was easygoing, the AND gate is its complete opposite. It's really, really strict. It will only give you a 1 if and only if both of its inputs are 1. No exceptions.
Think about it like this. Zara and Sophia want to play badminton. Can they play? Well, they can only play if Zara brings her kit and Sophia brings her kit. If just one of them forgets, the game is off. It's a true all-or-nothing situation.
And you can totally see that strictness right here in its truth table. Look at all those zeros in the output column. The only, and I mean only time the AND gate gives a 1 is in that very last row, when both input A and input B are 1. The symbol for the AND gate is this classic D shape.
I like to think of that flat back as the strict barrier for the inputs. It's a solid shape, which is perfect for its very solid rule.
So there you have it. Not, or, and. Now, they might seem a little abstract, but here's the cool part. Once you know their rules, you start to see them everywhere, even in really simple, everyday things. So let's try a quick puzzle. Imagine a house with two doors, a front door and a back door. Each door has its own doorbell switch, and the rule is simple. The bell rings if at least one of those switches is pressed. Okay, so based on what we just learned, which one of our three gates is running this doorbell? Think about that key phrase. The bell rings if the front switch or the back switch is pressed.
You got it. It's the OR gate. If you guess that, you're absolutely right. It's the perfect logic for this. An input from either switch or both results in an output, which is the bell ringing. See, you're already thinking like a computer engineer.
So, what's the big takeaway from all this? Well, it's that every app, every video game, every piece of complex software, it all boils down to combining these three simple rules, billions and billions of times per second. It's staggering complexity built from the absolute simplest foundation. Which leaves us with a pretty deep question to think about. If our entire digital world is built from nothing more than a massive chain of simple yes or no decisions, what does that really mean for the future of intelligence itself?